Welcome to the Walton Pie. Today we are going to go through a related rates problem. But this is even better than a related rates problem. This is a story related rates problem. So if you haven't already, please consider liking and subscribing and check out a lot of my other videos. It really does help me out to be able to keep making these videos to help explain mathematics. So here we are. Our nightmare situation. We have become the math problem. Okay? So in a fit of anger, after seeing the ridiculousness of all these different questions that I'm asking you, you decide to track down my address at 314 Euler Road in Mathlandia, and you decide to cover my property with toilet paper. However, just as I have planned, the things that I've been asking you and explaining to you have begun to seep into your mind as you start to throw the toilet paper. So you notice that you can throw the toilet paper exactly 15 meters per second, and that gravity is exactly 5 meters per second squared. You're still not entirely sure how that's possible, since you know that on Earth it's like 4.9 meters per second squared, but somehow I've managed to distort the gravity around my property, and so you're not entirely sure how gravity is exactly 5 meters per second squared. But you do just somehow know that that's what it is. You're not entirely sure how you know, but you know? Okay, so on a whim, because you are becoming your own worst nightmare. Who wants to go and do this? But on a whim, you measure the toilet paper, and you realize it has a diameter of 13 centimeters, and that there are exactly 40 sheets of toilet paper that stack together to be 1 centimeter thick. You shrug and okay, I don't need to know this. I can just put that out of my mind, and you start to throw the toilet paper anyway. And then suddenly, tragedy strikes. Exactly 2 seconds after you threw the toilet paper, you ask yourself, how fast is the diameter of the toilet paper shrinking right now? And then you pale. Oh no. I have become the math problem. So, unable to move, you decide, I need to solve this, and then I need to get out. I need to get out of Mathlandia before I become the person who's buying 1 million watermelons and trying to figure out how to stuff them in a car. We need to solve this problem and get out as fast as we can. So, how fast is the diameter of the toilet paper shrinking? Now, we're assuming that the toilet paper is unraveling as it gets thrown, and the way that we're going to assume that it unravels is that as you throw the toilet paper, there we go. So as you're throwing the toilet paper, so here's the toilet paper roll, it's unraveling, we have part of it, and we are going to assume that the very bottom of the toilet paper, that is always on the grassy lawn at the very bottom. So as you throw the toilet paper up, it's going like this, but the toilet paper is unraveling, so it's always touching the ground. Okay, so that's how we're going to be setting up this problem. So how do we solve this? We're going to need to try and figure out what exactly is going on. Okay, so somehow this is going to connect to some sort of related rates. There's different things interconnected. How do we solve this? Okay. So let's try and figure out a few different things. We're going to need to break this down into a few different pieces. First, what we're doing is we are starting by throwing the toilet paper straight up at 15 meters per second. And then this is 2 seconds later. So 2 seconds later, it's at this height. And now what we're trying to do is we're trying to figure out what's going on. So the first question we might ask is, how fast is the toilet paper traveling after 2 seconds? So let's approach that problem first. So let's slide on over and try and figure out what's going on. So we have our diagram. It's going up, and then we are trying to figure out what's happening. Well, we know that gravity is equal to 5 meters per second squared, and gravity, that is an acceleration. Which means that we need to go through and figure out, well, if gravity is 5, and I know that the derivative of velocity is acceleration, what's a function whose derivative is just 5? Well, I'm going to say that my velocity as a function of time is going to be equal to the original 15 meters per second squared times the time, well, let's see. So it's 15 meters per second. Oh, just 15 meters per second. That's how fast I originally threw it, but then gravity is going to be slowing it down. So I'm going to then be losing 5 meters per second every second. So that means my velocity as a function of time is going to be 15 minus 5t. Okay, so that means we can now know what's the velocity at the time we care about. Well, the velocity at the time we care about is 2 seconds. So that means the velocity at 2 seconds is going to be 15 minus 5 times 2. So that's 15 minus 10. So that is going to be equal to 5. So at this specific instant that we care about, it is moving upwards at a velocity of 5 meters per second. And we also are going to need to know how high up is it? Well, remember that the derivative of position is velocity. So that means we need to have a function whose derivative is 15 minus 5t squared. Now, that's going to be a little bit tricky, so I'm just going to give it to you. The position as a function of time is going to be equal to 0 plus 15t minus 5 halves t squared. Don't worry if you don't know how to do that yet. That is going to be what we're going to be talking about in a couple weeks when we are going through stuff with antiderivatives. So don't worry about that yet, but that's what we have currently. So what we can do is we need to know what's the position at time t equals 2. So our position at time 2, that is going to be equal to 15 times 2 minus 5 halves of 4. So that's going to be 30 minus 10 is 20 meters. Wow, you got a really good arm if you're able to throw it that high. So there you go. 20 meters is how high up it has gone. So now we've figured out the position of the toilet paper roll. Let's go back and try and figure out what else are we going to need. Alright. We're going over here back to our question. So there we go. We have all the different things that we need. We are trying to figure out all of the different stuff left that we need. So we can throw the toilet paper at exactly 15 meters per second. So we've accounted for that in our picture. Gravity is exactly 5 meters per second squared. We've accounted for that. But now we're trying to figure out how can we figure out how fast the toilet paper is shrinking. So what do we need to do? We are going to need to somehow relate the rate that the diameter of the toilet paper to something else. Okay? So now here's how we're going to be doing that. We know how much toilet paper has been pulled out. We know it is 20 meters long. And we also know how much it was originally. So now how are we going to figure out exactly how long it was? Well, here's going to be the little bit of trickiness that we're going to have to figure out. So, come on, so let's draw a toilet paper roll real quick. So here we go. We got our toilet paper roll, and we have a whole bunch of different sheets inside. Here we go. We got a whole bunch of these sorts of things. There we go. So now what we're going to do is let's label these different things. We have a few different squares of toilet paper that are here, and toilet paper, I actually did measure this, is 10 centimeters across. Diameter is 13 centimeters, so all of these are the actual dimensions. And now what we're going to do is we're trying to figure out how much of the toilet paper has come off. Well, we know that the total distance is 20 meters, so what's the volume of that toilet paper? Well, the volume is going to be the 20 meters by 10 centimeters, and then the thickness is going to be 1/40th of a centimeter thick. So let's convert everything to centimeters. So that's going to be 2,000 centimeters. And so the volume that has been taken out is going to be 1/40th times 10 times 2,000. 2,000 divided by 40, that is going to be 50. So 50 times 10 is 500. So the volume is 500 cubic centimeters that has come out. And now the question is that all of the toilet paper? Well, let's figure out what's the original volume of the toilet paper. So volume of a cylinder is going to be not 4/3, that's of a sphere. So volume of a cylinder is pi radius squared times the height. In this case, the height is 10. Radius is going to be half of 13, so that's going to be a 6.5. And then a pi. So volume is, and we're going to say that pi is about 3 just to get a rough idea. And because of the inside piece, let's just round the 6.5 down to 6. So volume is about 3 times 6 squared times 10. 3 times 36 times 10. 36 times 3, that is 108 times 10. So that's 1,080 cubic centimeters. So we did not use up all of the toilet paper, which is good. Okay? So now what we're going to do is trying to figure out how fast is the diameter of the toilet paper shrinking. So let's go, and that was just a rough calculation to make sure we didn't use up all the toilet paper. Now we're going to need to know what is the current radius of the toilet paper. So the current radius of the toilet paper is going to, here, let's, I'm getting ahead of myself. So we're trying to figure out the rate that the diameter of the toilet paper is shrinking, which means we need to have some sort of connection between the diameter of the toilet paper and the height that it's up, because the height directly connects to how much of this toilet paper has been pulled off. And so let's go and tie those different things together. So let's just take this a little bit slower. So the volume is equal to pi r squared times the length, which is going to be the 10. So volume is 10 pi radius squared. We want to have some sort of connection to diameter. Diameter is 2 times the radius. So we can then say that diameter over 2 is equal to the radius. So we can use that here to get that the volume is going to be equal to 5/2 pi diameter squared. So now we have some connection between diameter and volume. But we also know how much volume is going to be used up. We know that the volume of the toilet paper that's been pulled out, so volume of our strip versus volume of the cylinder. So the volume of the strip, that's going to be equal to our height times 10 times 1/40. So this is equal to h over 4. So there we go. We have some sort of connection between the volume of the strip and the volume of the cylinder, and we know the connection between both of those together. We know that the volume of how much toilet paper has been pulled out plus the volume of how much toilet paper is still in the roll has to be equal to the original amount of toilet paper that was there, which is equal to the pi times radius, 13/2 squared, times the length, 10. So we know for a fact that is how much there needs to be, which means this is a constant, we have a connection with height, and we have a connection with diameter. We can tie everything together. So let's put all of that together. So we know that, let's see, 10, so we know that pi times 13 squared, that's 169, times 10 over 4, so that's the total volume. That has to be equal to 5 pi over 2 diameter squared plus the height over 4. Okay, here's where we're going to be able to tie everything together. We know how fast the thing is going up, which is telling us how fast h is increasing. So we know it's going up at 5 meters per second, which is 500 centimeters per second, which is how fast h is changing. That's the derivative of height with respect to time, which means we can now get a connection to the diameter, which I'm going to now just change to be a capital D, just so that we don't have a little bit of confusion with that. Okay, how do we go through and do it now? Now what we're going to have is we need to find a connection And the way we do this is through implicit differentiation. We are going to take that expression that we just found, namely that 1,690 pi over 4 is equal to 5 pi over 2 d squared plus h over 4. And we are going to take the derivative of everything with respect to time. Now notice that the original volume actually all just cancels out when we take the derivative, and that just goes to 0. But then when we take the derivative of the other side, we get 5 pi over 2 times 2d dd dt, so that's a d dd dt, plus 1/4 dh dt, and we know what dh dt is. So that means that 0 is equal to 5 pi d dd dt plus 1/4 times 500. Okay, that means all we need to know now is what's the diameter at the specific time we care about. And to do that, that is going to be going up to our original equation, which we actually just wrote right here. So that means we also can solve for what d is. So when we solve for d, we know what height is, so we know that 1690 pi over 4 equals 5 pi over 2 d squared plus the height in centimeters is 2,000 over 4. 2,000 over 4, that is plus 500. Okay, so that means that d squared is equal to 1690 pi over 4 minus 500 all over 5 pi over 2. So d squared is about, let me pull up a calculator and figure this out, because I'm not going to want to do this exactly. We're just carrying approximate. So let's see, here we go. What is that number? So 1690 times pi divided by 4 minus 500. So that is 827.3 divided by okay. Here, let's just actually just write the whole thing at the end. Okay, so divided by 5 pi over 2. 5 pi over 2. D squared is about 105.34, which means that D is about 10.26. Okay, so there we go. We have the diameter at that specific instant. So we can take that and plug it in, and we can solve for what dd dt is. So 0 is equal to 5 pi times 10.26 dd dt plus 1/4 of 500. So that's 125. So that means that dd dt is equal to minus 125 over 5 pi times 10.26. Let's figure out what that is, and then that gives us what dd dt is. So we get, let's see, it is a minus, okay, minus 125 divided by 5 times pi times 10.26. That is negative 0.7756 centimeters per second. So it is shrinking pretty quickly, which makes sense because you chucked that toilet paper at a ridiculously high speed. So all of that work was to answer how fast is it shrinking right now? Well, it's shrinking at 0.77 essentially centimeters per second. That is how fast the toilet paper is shrinking at this specific instance. Okay, I hope that made sense. I hope you enjoyed that problem as much as I did, even if it was probably a little bit harder than we needed it to be, but I thought it was a pretty fun type of problem. So yeah. I hope this video was helpful. If it was, please check out some of my other videos. Please like and subscribe if you haven't already. Please let me know what other types of math videos you would like to see more of. And I hope to see you all in the next video. I hope you have a great rest of your day, and good luck with all of your math.